So before I get into this, I would like to mention that no sound is random. A firing order or a cylinder count that has never been done is not going to create a sound that cannot be predicted in some way. I would also like to mention that I will explain this phenomenon in a way that is simple and understandable to those without extensive knowledge in music theory. I will be using 4-strokes for simplicity, and I will get to some other things towards the end of the video. So without further ado, let's get right into this. There are two distinctive characteristics in an engine's sound, and one of these, which is the least determining factor, is the overall pitch that the engine is making. When you have a cylinder delivering a specific number of power strokes per cycle, a frequency, which is measured in hertz, will result. Hertz stands for pulses per second and is how sound is measured, since a sound wave consists of just that. If you keep adding cylinders, 2, 3, 4, 5, 6, you will have more power strokes per cycle, or pulses per second, generating a higher frequency at any given RPM. What this means is that yes, at the same RPM, a 6-cylinder will be higher pitched than a 5-cylinder, which will be higher pitched than a 4-cylinder, and so on. What this also means is that you could get a bunch of different engines with different cylinder counts at different RPMs to all technically produce the same pitch, but none of them are going to sound the same because it's the harmonics of not one, but two frequencies that make each engine sound distinctive and unique from one another. It's also important to know that none of these engines will be delivering power strokes the same phase apart. More on that in a bit. So, every engine produces two tones. The bottom tone is the same on every engine, and the top tone depends on the number of cylinders there are. This creates an interval between the two frequencies and can be discovered by using a simple formula. To find an engine's sound signature, you take the highest octave of the crank speed underneath the tone of the cylinder count. This gives us a mathematical ratio. 1 cylinder, a frequency, 2, 4, 8, and 16 cylinders, 2 to 1. 3, 6, and 12 cylinders, 3 to 2. 5 and 10 cylinders, 5 to 4. 7 and 14 cylinders, 7 to 4. 9 and 18 cylinders, 9 to 8. 11 and 22 cylinders, 11 to 8. 13 and 26 cylinders, 13 to 8. 'And etc. So 2 to 1 means that the top tone is exactly twice that of the bottom tone, or 100% greater. 3 to 2 means the top tone is 50% greater than the bottom tone. 5 to 4 means the top tone is 25% greater than the bottom tone. 7 to 4 means the top tone is 75% greater than the bottom tone. So why does this happen? I will explain, but before I get to that, it is important to know that these musical intervals aren't being created by two harmonic series on two different frequencies an interval apart like they commonly are in music, but rather multiple series on the same frequency intertwined in phase as to give the impression of a musical interval by bringing out certain harmonics and subduing others in the final sound. To elaborate, in music, playing two keys or two strings on an instrument at two different frequencies or notes will create an interval. Well, that doesn't happen here because we have engines of multiple cylinders, and it's not like there is one cylinder on one frequency and one cylinder on another. But every cylinder goes bang to make sound, and that bang is the same bang on every cylinder. meaning that they all produce the same fundamental frequency. It's the way that the 5, 6, 7, 8, 9 cylinders sing together, almost like a choir, in their unique phase that creates these musical intervals. So basically, they're the same intervals, just created in a different way. Time to explain. So you have a one cylinder. This one cylinder engine delivers a power stroke every 720 degrees. This action generates sound, being a frequency in the measure of hertz, which equates to pulses per second, as mentioned earlier. The higher the RPMs, the more pulses per second, so you get a higher pitch. The lower the RPMs, the less pulses per second, so you get a lower pitch. You now add another cylinder and have two. This two-cylinder delivers a power stroke every 360 degrees. This means double the frequency, so at any given RPM, the overall pitch of the engine will be double that of the one cylinder. But more importantly, a 2-to-1 pitch ratio will also occur. So the sound this engine makes is the octave. Now, as long as we keep doubling the amount of cylinders from here, we are going to maintain that same pitch ratio. When an engine has 4 cylinders, the highest octave of the crank speed occurred when the engine had 2 cylinders, and there is a tone being generated by 4 cylinders, yielding a 4-to-2 ratio, which can just be simplified to a 2-to-1 ratio. The two frequencies being highlighted, the octave in this case, are now just an octave higher than they were before, since all that happened was that gaps in the cycle were filled in. Power strokes at 360 degrees apart every 720 degrees are now occurring every 180 degrees. With 8 cylinders, the highest octave occurred at 4, and 8 cylinders are producing power strokes every 90 degrees. 8 to 4 also simplifies to a 2-to-1 ratio. 16 cylinders with power strokes every 45 degrees yields a 16 to 8 ratio, which again simplifies to 2-to-1. This means that any cylinder count that is not a derivative of the two-cylinder series cannot possibly have the same harmonics and will inevitably produce its own unique sound. And this is where things start to get interesting. The 3-cylinder. The highest octave of the crank speed is 2, just like in a 4-cylinder, but instead of a tone being created by 4 cylinders, there is a tone being created by 3 cylinders, which yields a 3-to-2 ratio, the perfect fifth. Just like in the previous example, if we keep doubling the cylinder count here, we will get the same results. 6 cylinders yield a 6-to-4 ratio since the highest octave of the crank speed is now 4, which can be simplified to a 3-to-2 ratio again. 6 cylinders meaning that both frequencies of the perfect fifth are twice the pitch at any given RPM than they were in the 3-cylinder, since gaps were filled in the cycle. 12 cylinders yield a 12-to-8 ratio, which again simplifies to a 3-to-2 ratio, creating a perfect fifth at twice the pitch at any given RPM of the perfect fifth in the 6-cylinder. Now that you get the basics, it is time to truly explain this phenomenon. If you look at the ratio created by the phase of power strokes that corresponds to any given engine, you will find that it yields the same mathematical ratios as the formula mentioned earlier. Let's crunch some numbers. A 1-cylinder fires every 720 degrees of crank revolution. A 2-cylinder fires every 360. What is 720 over 360? 2. 2 over 1. 4 cylinders, 180 degrees. The highest octave of the crank is 2. What is 360 over 180? 2. 2 over 1. 8 cylinders, 90. 180 over 90. 2. 2 over 1. 16. 45. 90 over 45. 2. 2 over 1. A 3-cylinder, 240 degrees. The highest octave of the crank is 2. What is 360 over 240? 1.5. What is 3 over 2? 1.5. It's the same. 6. 120. 180 over 120. 1.5. 3 over 2. 12. 60. 90 over 60, 1.5, 3 over 2. A 5-cylinder, 144. The highest octave of the crank is 4. What's 180 over 144? 1.25. What's 5 over 4? 1.25. 10, 72. 90 over 72, 1.25. 5 over 4. A 7-cylinder, 102.85. What's 180 over 102.85? 1.75. What's 7 over 4? 1.75. 14, 51.42. 90 over 51.42, 1.75. 7 over 4. You get the gist. Now let's get into some other factors that can affect sound. Two strokes. Two strokes aren't really different in any way, only difference being that all strokes are accomplished in 360 degrees instead of 720. So at any given RPM, a two-stroke engine of any number of cylinders will be twice the pitch of a four-stroke since the same number of strokes are occurring in half the distance and time. What about rotaries? So a single rotor completes 3 power strokes for every 1 revolution. Now you may be thinking it should sound like a 3-cylinder, but it doesn't, because the output shaft rotates 3 times every time the rotor makes a full revolution, which means for every power stroke, the output shaft rotates once, giving a 1-to-1 ratio, not 3-to-2. You can probably see where this is going, but let's crunch the numbers anyway. A 1 rotor fires 3 times for every full revolution of the rotor, which is accomplished in 1080 degrees of output shaft rotation. So there are 360 degrees between each power stroke. So 1 every 360, or 360 times 3, a 1-to-1 ratio. A 2 rotor, 3 every 540, or 180 times 6. 2-to-1, since 1080 over 540 is 2. 3 rotor, 3 every 360, or 120 times 9. 3-to-2, since 540 over 360 is 1.5. 4 rotor, 3 every 270, or 90 times 12. 2-to-1, since 540 over 270 is 2. 5 rotor, 3 every 216, or 72 times 15. 5-to-4, since 270 over 216 is 1.25. Any math you use, the numbers will come out the same. But it looks oddly familiar, doesn't it? This is why 3 rotors, for example, sound a lot like 6 cylinders, but with the typical rotary sound or rotary timbre. Pistons and rotaries will have a different timbre because the sound isn't being produced in the same exact way. More on those qualities later. Firing orders definitely have an impact on an engine's sound, but the effect they have is more or less changing the qualities or characteristics of the fundamental sound. A 6-cylinder, no matter the firing order and no matter the layout, will sound unmistakably like a 6-cylinder. These slightly different qualities could be described as the perceived weight, color, or brightness. Some are lighter and brighter, some are darker and heavier, some are smooth, and some burble. These are qualities that are usually used to describe human voice, but they can be used to describe the sound of engines too. Another good example of this would be if you played the same note, let's use a G2, on 2 different instruments, a 4-string bass and a cello. You will be able to distinguish the 2 from one another even though they are playing the same frequency because they are producing that sound in slightly different ways. Headers and exhausts can also alter these qualities. Headers of different styles, lengths, angles, and diameters, exhausts of different lengths, angles, and diameters, even materials, will also play a role in which harmonics are highlighted and which ones are not. This is why, for example, there can be a V6 that has an exhaust that sounds great and a V6 with an exhaust that sounds terrible. The sound a V6 makes is fundamentally consonant, But some types of headers and exhausts can bring out certain harmonics and overtones that don't blend well together, and dull certain harmonics that would blend well together, so you wind up with something that should sound good, but doesn't. It all depends on how the engine's harmonics interact with the unique characteristics of the headers and exhaust. Engine layouts, which have different firing orders already, usually have different types of headers, which will impact the way the exhaust pulses are scavenged and at what rate they will enter the exhaust, so you can expect similar results. Modern McLarens and Ferraris have sound engineers intentionally take advantage of these qualities so their otherwise identical sounding flat plane V8s will sound distinctive from one another. So the music system we are using here is known as 12-tone equal temperament, which is the most commonly used music system in the world and is called so because there are 12 keys between one octave to the next and all keys are evenly spaced apart. All the intervals possible in order are the minor second, minor third, major third, perfect fourth, tritone, perfect fifth, minor sixth, minor seventh, major seventh, and the octave. Some intervals sound similar to others due to something called chord inversion, where the bottom tone becomes the top tone or the top tone becomes the bottom tone. This means the fourth and fifth are inverses of one another, so are the third and sixth, and the second and seventh, with perfect intervals staying perfect, majors being inverses of minors, and augmented intervals being inverses of diminished intervals. As you could see from the screen earlier, none of the intervals created by these engines have direct inverses. So this means that 7, 14, 9, and 18 cylinders will sound somewhat similar and give the overall same impression when heard, but will not be as similar as the inverses on the piano keyboard or as similar as the real inverses of the sounds that these engines make. The same goes for 5, 10, 13, and 26 cylinder engines, and 3, 6, 12, 11, and 22 cylinder engines, although the former two examples will be much closer than the latter. All in all, every engine will retain its own unique harmonics and character since none of them have true inverses in engine form. So yes, an engine is a musical instrument because it creates organized sound by the use of firing intervals and firing orders. So next time you hear a car or an engine and you tell yourself that it's music to your ears, well, now you know that it really is. There is a cliffhanger, however, and it's that there are some exceptions to these rules, which I will cover in future videos. That's going to be it for this video. Thank you so much for watching.